Hey guys, welcome back to Rocket Gyan, my fellow space tubers, and today I am very excited, full of power, and I just can't control my feelings because today we are actually gonna see something very sci-fi, very such a thing which is only demonstrated in movies, series, and whatnot, but in real life we're gonna see it today. So this is double asteroid redirection test, or DART, as the name suggests. And as you know, NASA is like to the point, on the go when it comes to naming the acronyms for a mission. And this DART, as the name suggests, DART is like a dart only. They're throwing some sort of thing to an asteroid, so as to deflect it. So you just don't worry about like the mechanics of it, how will it work and whatnot, because I am here to explain you that. So you just sit back and relax and just enjoy this moment, historical mission, which will change the outlook of our space forever. We will be having if this is successful, we will be having a planetary defense system in place. How cool is that? Planetary defense system. Just saying it out loud is just, gives me chills. So, all right. Welcome to this stream. Wildflower, welcome. And Michelle Powell, welcome to the stream. I'm curious, what if the asteroid is less than they think? Like how the one we landed on was more. What's the word? Powder. Yeah. Okay. So talking about this, I know this sort of doubt will come to your mind. So I have that for you covered already, so you don't have to worry about it. Uh, what you need to worry about right now is just clicking on that like button and maybe sharing this one with your friends, because this is like the topmost historical mission of this year. If the Artemis does not launch, this will be it. So right now we are T-2, just a second, 2 hours 1 minute. I'll adjust the clock, so don't worry about it. 2 hours 1 minute, almost 2 hours 2 minutes from the impact time. And this is just this. Let me just get into this mission only and explain you um by looking at it, right? So yeah, so this is the DART mission, or double asteroid redirection test. It's not like they are hitting two asteroids, that's why the double asteroid name. They are not hitting two asteroids, but instead they are hitting a binary system of asteroids. So there is an asteroid which has a moon on it, and we will be hitting the moon of it, so as to check whether we can change the orbit of a certain thing by using kinetic energy. So it will be a kinetic impactor. So let me just show you how this works and what it would look like. So yeah, this is the thing. So we are going to the asteroid Didymos. So this is the Didymos asteroid, which is the you can say the parent body, and then we have a Dimorphos, which is the moon, or you can say, I would say, the moonlet, because it's very tiny. But how cool asteroid is this? It has its own moon, because asteroids does not have its own moon, but this one has. So how cool is that? And also look at this uh, this thing. Like, you might be wondering, how can an asteroid have its own moon? So first of all, yes, asteroid can have its own moon, because the orb it has a gravitational pull, and if something is in its orbit at a certain speed or an orbital velocity, it will stay in the orbit, right? But the thing is, it's a very unique system, because asteroid is very I mean to say, the surface texture, or surface feature, I should say, is very bad. I mean, it is very rugged. The imperfections are there, which causes the orbit of anything around it to lose its shape. But that is not the case with the Dimorphos. But we are doing something that will change the orbit for it for forever. So yeah, sorry, Didymos, but we have to do it to save our species, right? We don't want to be buried like our ancestors, dinosaurs, right? So we need to do something. So yeah, let me just explain you. So this is a Dart spacecraft. So this is a kinetic impactor mission. So what does that mean? It means that this will just head on collide with an asteroid, more specifically with its moon, to change the orbit of the moon. So technically it's not changing the orbit of the asteroid, it's changing the orbit of the moon. So what they want to actually know and understand is whether it is even possible to just hit the asteroid, or yeah, the asteroid, so that they can change the kinetic energy of that asteroid in a specific way, in a very precise way, such that they can calculate it and accordingly change the velocity of that asteroid, so that it just misses out of the earth if any asteroid is coming to the earth right now. So there is this thing. So what it will do is the start mission, the Didymos, and there is Dimorphos. So Dimorphos is the moon of this Didymos. The Dart mission, the Dart spacecraft, will just head on collide with this Dimorphos moon at speed of around 15,000 miles per hour. So it's, you know, almost close to the orbital velocity of the earth. And yes, it will just keep on it has its own navigation system, everything, which I will also talk about, but it will just hit on to the this Dimorphos, so that it changes the orbit of this Dimorphos, and taking out the kinetic energy. So it will, like, you know, the Dimorphos, let's say it's, yeah, it's the orbit is like this, and in this direction, so it is having velocity in this direction, but the Dart is going in this direction. So therefore what will happen is the since the kinetic energy is being applied in the reverse direction, so it will slow the velocity down. Means not slow the velocity down, that's not the case. What it will do is it will kind of act as a retrograde engine for this Dimorphos, which means it will decrease the orbit of the Dimorphos. And here you can see if the impact is successful, the new orbit is there implied in this new blue lines. So what it will do is it will change the orbital period. Right now it's almost around 12 hours, this orbital period of this moon. It's almost around 12 hours. By hitting it, we are like looking forward to change the orbit of it by like 11 hours and 45 minutes. So we are trying to make it move faster. So it might look like, you know, we are imparting some what should I say, velocity in reverse direction, but then also we are getting like uh, um, new orbit which is faster. So it's orbital mechanics. So, and it works like that, because what you are doing is, let's say you are imparting an engine, right? It's an engine only here, and it's imparting some velocity in this direction. So it's trying to slow itself down, but by slowing itself down, it will be increasing the velocity, because the perigee of this orbit will come down, and since the perigee is coming down, so the orbital velocity, the orbital time period will increase. So if it is like going out of your mind or just going above your mind, just remember this: going to hit the moon and not the asteroid, and it will try to change the orbit of the moon of the asteroid. So if you ask me now, why aren't they hitting the asteroid, right? It's like also there is this Licia cube which we will talk about, so don't you worry about it. But the question first of all arises, like, why are we hitting the moon but not the actual asteroid? Because we can precisely measure, this is a test ground, right? And when we are testing something, we need to measure something. We should be able to measure properly. So we will be able to measure the orbital period of this Dimorphos, because this asteroid is specifically chosen at this time period because it will be closest to the earth, almost like 500 million miles, if I'm not wrong, right now, closest to the earth. So the earth based telescopes will be able to observe the this moon Dimorphos, because the Earth-based telescope can distinguish between this Didymos and Dimorphos. It's like a big light blob for Didymos and a small light blob for Dimorphos. So it's like, when it goes around the when comes in front and then it goes around, you can detect that light moving in a certain direction in around this Didymos. Using the telescope, so you can actually precisely measure what's the orbital period by counting the pixels and how much it has moved in a certain period of time. So if the orbital period is decreased, then the mission would be successful. So this is how the mission will look like. But now let's have a look at this spacecraft, right? This Dart mission spacecraft, the double asteroid redirection test spacecraft. So this is the spacecraft. This has its Draco cameras, which is kind of derived from the New Horizons LORRI camera. So this is a very capable camera. It has been featured in this one also, and in the Lucy spacecraft also. It's a very capable camera for these kind of maneuvers to identify an object or a planet or a celestial body from a long distance, and then make some calculations according to that image. So this is the actual spacecraft. And if we look on to when it is in the space right now, so how does it look like? It looks like this. So it has its solar arrays, and if you look at this one, these are the roll-out solar arrays and not the normal ones. So there's that, because they need these solar arrays because the propulsion system is an electric one in here. So they need lot of electricity and whatnot to make sure this satellite can run on electric power, and that is the reason why they need large solar arrays. But the problem is, if they will go with the large solar arrays, the weight will increase, and you need to minimize that. And this roll-out solar arrays, if successful, and now it is proven to be successful because it is still running and everything is going all right, it will be featured in other spacecrafts also, where the weight is the primary concern, because most of the time when in the electrical spacecraft, weight is the primary concern, and these solar panels do a great job in mitigating that. So yeah, this is the one. It does not have any as such scientific equipments. We will get to the science also, like what are the objectives of the mission, but right now it does not have any as such spectrometer or something like that to do something, but Licia Cube has. So yeah, we'll have a look at it. But now let's just have a look at this the guidance and navigation system of here. All right, so this guidance and navigation system for this spacecraft is truly amazing. But before that, let's have a look at this spacecraft in much detail. Okay, so let me just go back a bit. Okay, yeah, so let's have a look at the mission properly, and have a look at like what all is supposed to happen and everything, so that you get a hang of things. So this is I have already explained you right now, like what will happen, everything and whatnot. This is the Dart's target is the binary asteroid system Didymos, which means twin in Greek. So Greek friends out there, shout out to you. And the system is composed of two asteroids. The larger asteroid Didymos, so diameter is 780 meters, or almost half a mile. So it's not a very big asteroid, but still it's a half a mile asteroid. And the smaller moonlet asteroid, you can say that, is just 525 feet. So there's that. And this was launched from the SpaceX Falcon 9 rocket from Vandenberg Air Force Space Station. Air Force Station, yeah. So this Falcon 9 rocket lifted off in November 2021, and now it has reached now it will be reaching and impacting the asteroid. So there's that. And we all know the partners and collaborators. I'm not going on to that. So let's have a look at the impactor spacecraft itself. So this will give us the dimension, the proper thing, what this spacecraft looks like. So it's almost like 1.2 into 1.3 into 1.3 meters in dimensions. It's not a very huge spacecraft, almost comparable to a small car which you have. And it only weighs around 570 kilograms at impact. So it was obviously much heavier when it launched, 610 kilograms, but it has used that xenon gas which it uses for electric propulsion system in here. So therefore the the weight has decreased, so 570 kilograms at impact. So it carries both hydrogen propellant as well as for spacecraft maneuvers and attitude control, and xenon. So if you are worrying why hydrogen, so there is when you are impacting an asteroid at almost 15,000 miles per hour, you need to be controlling your attitude and make sure the corrections are in proper dimensions. And for that you need a propellant which is kind of act as a reaction control thruster, and in that case you use this hydrogen propellant, just like a Dragon. In the Crew Dragon we have those Draco thrusters, Super Draco thrusters for our bot system, but Draco thruster we have that also uses hydrogen. So similar to that, those hydrogen does give a good amount of thrust in a small period of time. So that's why it is used. So the payload on this one, as I said, is a Draco. So this Draco is a high resolution imager derived from, as I said, a New Horizons LORRI camera to support navigation and targeting to measure the size and shape of the asteroid. I'll talk about the actual navigation. It's very cool when you will have a look at how the system works. If you are a software engineer watching it, you will love it, because if you will know like how the system works, how it gathers the information, then reduce it, and then correct its maneuvers and whatnot, you will get a very nice look at how the Smart Nav system is coupled with this Draco camera. So we'll talk about that. Then this Lycia cube. So this is developed by Italian space agency. The name is Light Italian CubeSat for imaging of asteroids. So it was already deployed from the spacecraft 15 days ago. Yep, it was already deployed from spacecraft 15 days ago, and its main purpose is to capture images of the Dart impact, the resulting ejector cloud, and potentially a glimpse of the impact crater on the surface of Dimorphos. So it's like when you have impacted, so you can't obviously use the cameras of the Dart mission because it will be destroyed and everything. So you need to have certain sort of imager, the cameraman. So it's sort of a little cameraman which has already been deployed 15 days ago. So it's been floating. It has already gained separation of around 50 kilometers or so, and after this impact, it will come to the destination, image the spacecraft. Not the spacecraft, obviously it won't be there, it will be dead like a rock. But the asteroid, the ejector cloud, whatever is being ejected from this asteroid, and the impact side, how the impact looked like, whether it has changed, whether it has totally disintegrated the moon or something is still remaining. We'll get to have a look at that. So this is a great you can say a lifesaver, right, to know what actually happened out there. Okay, so there's that. And then we have the technologies, the GNC and smart navigation system, which I will obviously talk about. GNC is nothing but the guidance, navigation, control, and smart navigation. So this smart navigation is actually derived from those they have taken the help from the Air Force missile system, because it will be going at around 15,000 miles an hour, almost like a missile is going like that only. So they have taken this navigation system derived, I would say, from the missile navigation system only, so that it can hit the target properly without any problem. So this is a smart autonomous system, and yes, there is a delay of around 38 seconds for the light to travel to there and come back. So this because of this 38-second delay, you can't have a joystick with the live feed going around, right? You can't do that. So that's why you need to have some sort of autonomous system, and there's the work of software engineers comes in, and machine learning and artificial intelligence, to make sure that the spacecraft is smart enough, can make its decision in split second, so that it hits the target accurately. So yeah, there's that, and then the we know obviously about the propulsion system, and yes, the rollout solar array. So it is already in use in the ISS. It was launched on Crew Dragon only, and it's already in use in ISS. It's working pretty well, and it was also used in this mission. So yeah, and they also tested another set of array which is known as transformation solar array. So this is like this is a high efficiency solar cell, provide 3 times more power than current solar array technology, and if successful, which it is already, which I think is already is, it will be able to make sure the solar panels can be scaled down and still perform accurately. So yeah, there's that. Then we have this high gain antenna also, it's in this there we have this avionics unit. So yeah, this is almost pretty much about the spacecraft that you needed to know. And yeah, we'll have a look at this one also, so don't worry about it. But let's have a look at the asteroid system right now. What will be the speed of the impact? So yeah, I'll have a look at your questions also. So this is the system, guys, in front of you. So this is like, yeah, so you can see it now properly. So this is the Didymos system. So this is Didymos spacecraft, this is Dimorphos, which you can see, and it is obviously right now rotating and having a good time right now. But it does not know that the Dart is coming onto its way, make for I don't want to say it actually, but their sweet little life of the moonlet might be destroyed today. But that's how we learn, right? So let's hope it's not totally destroyed, but just a little tickle, or experience just a little tickle on its ankle. That's what we are hoping for. Yeah, so this is the system which you can see in front of you. Let me take some questions if you have any. I'll talk about this powdery thing, so you don't you worry about it. Hey, hi Yushi, welcome to the stream. Hi Madam Eli, Sean McGuinness, Amy, Sergey, Giorgio, welcome all. And let me just target. Hello from France. Hello Charles. We know people are watching this. This is a historical event, and people are watching this one from all over the world, and you should be watching it. So yeah, we'll take more questions. If you have any, you can just totally type in the chat, but let me just complete what I want to say. So this is a system which you have seen. So now this is how it looks like when it orbits. It's more like, this is also rotating, the parent body, and the Dimorphos is also rotating. So again, now this, you can see the Dimorphos is moving in this direction. So the Dart spacecraft will come from this direction, let's say, and then hit on the Dimorphos moon like this. So what it will do is it will act as a small engine, or you can say, I won't say a small engine, but it would be an impulse. It will be an impulse on it, which will create, which will slow this Dimorphos moonlet down a little bit. But because of that slowing down, it will lower the orbit of this Dimorphos moon, which will cause the Dimorphos to have a increased time orbital period, and making it a little bit faster at perigee. So it's kind of a complicated thing in orbital mechanics. If you have played KSP, you know what I'm talking about. You are just taking energy out of the system, or by hitting it on the Dimorphos, and that's how you are lowering down the orbit, by taking the energy out of the system. And when you are lowering down the orbit, since it is going towards the gravitational body, the speed increases. That's how it works, and that's the reason why the speed increases, even though it's kind of getting slowed down. So it's orbital mechanics itself is like mind-blowing. You need to learn about it, and you don't need any high school, high intensity college degree to understand those things. Just high school physics will do that. Okay, yeah, so let's move on to the next thing, which is all right. So we have already talked about this. Yeah, now let's have a look at the guidance and navigation control system which I was talking about, right? So this is the it will this is the guidance navigation control, or you can say how the system will detect where the dimorphos is and where the didymos is, because system needs to differentiate between those two things, right? We are trying to hit the dimorphos, not the didymos. So there is that. So let's have a look at it. So it is this is what the asteroid is currently seeing right now. Okay, I'll show you. So we will also be getting the live feed from that Draco camera. So it will be like 1 frame per second, but we'll be getting some live feed, and this is how it would look like right now, because it's not in the view. But when it comes to the view, it will be having like a blob of light on this on its camera. So we'll have a look at that. So let me just this yeah, this is the thing. So it will be able to see the system, detect the system from around 54,000 to 62,000 miles, and from this distance a tiny maneuvering error could be the difference between hitting a dimorphos and racing past it. So you can see it just tiny, you can see almost the line is like intersecting with the actual hitting line, but it's not totally accurate, and because of that it misses it. So we don't want that, obviously. So for that we need to be very, very accurate, and yeah, so there's that. So like how it will be accurate and how it will do it. So there's this let me just show you the mechanism. Let me so yeah, so there's this Draco camera which I just showed you, the Didymos reconnaissance and asteroid camera for optical navigation, the Dart's eye, making sure it hits the target no matter what. And when you look at the thing which I'm trying to show you, you will actually feel like, yes, it's like a targeting system for a missile trying to hit a target. So yeah, there's that. Okay, let me just show you now. So yeah, this is what happens. So first of all, it will be blobbing detection of the blob. It will take the Draco image, which it does, then it will try to detect the blob from those images. So it will, once Draco takes an image, it forwards the picture to the detection, and blobbing will happen, which makes sure it is able to detect some light. Okay, now moving on to the next thing, which is known as centroiding. So centroiding means putting some X marks to the images. So you can see here, so there it will be able to put some X marks onto the moon as well as onto the asteroid itself. So once the asteroid blobs are identified, the centroiding algorithm finds the middle of each one, so that it will be able to make sure it can these crosses are pointing towards the middle of it. Okay, now next thing is the targeting. Now you have two crosses. Okay, now you need to identify which one is the target. So this is the targeting system to find the asteroid we want to hit. The targeting algorithm takes those two centroids and marks the smaller of the two, to make sure, yeah, that is the one which I need to hit. Okay, so the next step after that is this image processing is done. Now the system comes into the guidance and control filter. So this guidance filter will predict the future. So what it will do is, the guidance filter then deciphers where dimorphos will be in near future when it will hit it, relative to where the spacecraft is currently headed, and consider how the spacecraft should move so it remains on course. So it will predict where the moon will be when it reaches there, and make sure the spacecraft also reaches there, and the guidance and navigation control system takes over the spacecraft, making sure it does all those small corrections and hit the target. And then the second thing is maneuver logic. Once the guidance filter has make sure that, yeah, identified the target, everything, where it will be, then the maneuver logic comes in, taking the input as the guidance filter. Maneuver logic comes in, and it is fed into the computer system, and then yes, the system works. And then finally the autopilot takes in, making sure the maneuver logic is done properly. So this is the proper system. This was mind-blowing for me. Like, this is such a cool system. Obviously there could be something which can go wrong, but yeah, there's that. So if you look that on the map, so this is kind of, how the things would look like. So it will be as if it were taken over the Indy 500 when we stop maneuvering. So here they will stop maneuvering around 500 miles, and then we simply coast all the way to the Baltimore and land inside the Camden Yards. So this is the actual, what should I say, gist of what is going to happen. So yes, it will be costing. So it will just switch off its engine at around 500 miles, and it will coast towards the system, and I don't think so it will do any course correction here also in this 500 miles thing. So yeah, just hit it. So yeah, this is the code for it. Now if I move on, here also, this is the video which you can see, like this is a simulation video. So here you can actually see how the system would look like, and there's the thrusters working. There's which one, so that the spacecraft is hitting the target, so, and making sure it is going as per the plan. So here you can see how it would look like. If we move forward, you can see that blob is actually becoming larger and larger. So it has actually identified the target system is this one and not this one. So it is making sure, now you can see the thrusters are not firing that much because it is very close to the system. So here you can see now it is coming real close. You has already identified the system. The time to impact is just 7 seconds. It is 30 times the real-time image, but still you can see like how it is working. So yeah, it's coming in. Don't you think it's looking like a total this missile tracking system? So yeah, there's that. And now you can see the thrusters have stopped firing. So it has reached that 500 miles of altitude distance, and then just a smaller thruster fire here and there, making sure everything is going fine. And then boom, hit it there. We have mission accomplished, target is down. So this is how it would look like, the targeting system. Oopsie doopsie. Wow, I am just so noob. It. All right, I'll just explain it in a bit more funny way. So yeah, this is the thing which I was supposed to show you. I guess now you are seeing it. All right, I'll just wrap it up real quick. So yeah, so the guidance and navigation system which I was talking about was this one. Here you can see it, this is the Draco image. Is the Draco is nothing but a imager which will capture the image, and the blob detection will happen, which you can see in here, making sure it can identify the Didymos and the Dimorphos. Once it does that, then the centroiding system takes place, making sure those X marks are on the that image, and we have the centroiding means the X marks are on the center middle of each image. So after the centroiding is done, the targeting system comes in, making sure which one to hit, the bigger one or the smaller one. Smaller one is then identified and the target is set. After that, the image processing is done, and the guidance and navigation control system takes place. The guidance filter kicks in. What it does is just predicts where this moon will be in near future when it will reach this asteroid. So the state estimation is done by this guidance filter. Once the estimation is done, then the maneuver logic is generated using the state as a estimation and guidance filter as input. This maneuver logic makes sure the spacecraft actually hits the target, and yeah, then the autopilot kicks in, which takes maneuver logic as an input, making sure that maneuver logic is followed till the time of its death. So yeah, this is the guidance and navigation control system. So yeah, this is the code I was talking about. If you look at that on a map, it is as if we were over the Indy 500 when we stop maneuvering, and then we simply coast all the way to the Baltimore and land inside the Camden Yards. So this is the kind of analogy which Mark gave. of how it would look like when they are trying to hit the target. So yeah, there's that. And now I was talking about this video which you need to see. This looks like, you know, this is the video which I was supposed to make you see. Here's the thrusters are firing. Here you can see it has already identified the target, and this is the real time, making sure the feed of the what should I say, the camera, making sure it remains in the vicinity. So if I just move forward a bit, you can see it's now starting to grow larger, because it's coming near and near. And these are just the thrusters which are firing. There are 8 thrusters on it. They're firing, making sure it is right onto the target. And now it is coming really very close. You can see it's 30 times the real time, but still it's very close, becoming bigger and bigger. This is just a simulation obviously, but this is how it would look like. So becoming bigger and bigger, and finally it's like 1.5 minutes from the target. It's again becoming, now it's like, you know, 500 miles from the target. So the thrusters firing has just almost stopped, just a little bit of maneuvering here and here. And then finally at 5 4 3 2 1, and boom, you go. This is what I was talking about, like the missile tracking system. Yep, this is a simulated one. Oh, god. First of all, really sorry guys, I was like talking and talking and talking, but did not show you this amazing video which I was supposed to do. My bad, but this won't happen from now on. So yeah, okay, cool. So now let's move on to the next thing. Let's understand this Didymos in a bit more detail. So this system, Didymos and Dimorphos. So this is the asteroid system which you can see. So this Didymos is 780 meters. So this is a scale which you can see, and Dimorphos is like 163 meters. So Dimorphos is almost like, you know, almost the size of what should I say, the Great Pyramid of Giza, and a little bit bigger than the Statue of Liberty, which you can see. But this Didymos is way bigger. This is like, you know, bigger than the World Trade Center, and it's you can say kind of Burj Khalifa is slightly bigger than this Didymos. So it's a large asteroid. You can imagine now the scale of it, and if this size would have hit the Earth, oh god, not only we would have gone extinct, but almost like, you know, what would have happened, the ice age on the Earth would have again come. So the ecology system, everything would have been destroyed. Everything would have been like, you know, just that would be the end of the Earth for some time. So yeah, there's that. And we don't want that, and that's why we are developing this cool looking planetary defense system. And yes, this is how it would look like. So we will be observing the event using the telescopes on Earth. So we have chosen specifically this system because this is a binary system which we can easily map, easily test, easily measure, and also it is going very close to the Earth right now. It's on the closest approach, around 500 million miles if I'm not wrong. And this will hit this one, and this Licia cube will be there, hiding in a spot, making sure it images everything which has happened, and yeah, return those images back to the Earth. So this is how it would look like. Now let's have a just look at, like, you know, what all things will be observing it. So these are the telescopes which will be used. You can see from all over the world this event will be observed. They will be observing this asteroid for weeks after the impact. They want to make sure, because the ejecta will be there, and the ejecta will take a long time to settle down, and that's the reason why they need to study that ejecta and making sure everything is understandable basically. So yeah, there are like ton of telescopes which they will be using all over the world. And not only that, they will be pointing the James Webb telescope, they will be pointing the Hubble Space Telescope, and also the Lucy spacecraft, which is going to the Trojan asteroids, will be observing this event. So this is the importance of this event, and I can't just specify again and again, like how cool is this one. Okay, yeah, this is how it should look like. And now coming on to the main question which you just asked me, like powdery and everything. So we have already, let's have a just quick overview, quick summary of everything we have discussed, all this, so we don't need to worry about it. And what I need to show you is yeah, this is a planetary defense system. So in planetary defense, not only we just launch something and make sure it just gets destroyed or we can deflect it, but there are certain things which we need to do. We need to plan and coordinate, we need to mitigate by we need to assess, search, detect. So this works from search, detect and track. Once we have searched any asteroid, then we need to characterize those asteroids, whether it is harmful for us or not. And if it is harmful, then we need to plan and coordinate the mission. Then we need to make sure it is mitigated, the threat is mitigated. Once it is mitigated, we need to assess the situation, like everything is all right or not, whether we were successful or not. So this is the total system which it works. And yeah, this is also a thing which you can see. So an asteroid of size 4 meters, just 4 meters, it's like frequency is 1 per year, a bright flash, no ground effects, but could leave meteorites. So this is how it looks like. Then 25 meters, almost 1 per 100 years, air burst explosion could cause widespread injuries over populated areas. And it actually happened in I guess in 2011 or 2012 in Russia, where this around 25 meter size asteroid came to the earth. It exploded in the air, and the people, first of all, what happened when it exploded over the air, there was a huge light explosion, right there. It was even brighter than the sun at that point of time. And because of that, people at the homes, in the offices or in the schools, they just went to look like what is happening, why suddenly the sun has come closer or whatnot. And when they went there to see what has happened, it burst. So the light actually travels faster than the speed of sound. So what actually happened, they saw this light coming in obviously faster, but they don't know what is actually accompanying it, the sonic boom. So everyone went to their windows to see what is happening, and then the sonic boom came. Boom. Wow, all the windows and everything was shattered, everyone was on the ground, there were so many injuries because of it. And yeah, this is a dangerous situation to be in. So a good side note, if you are thinking sun is coming closer to the earth now, if you are feeling like that, please don't go out and look like what has happened. Just stay inside and make sure you are very much away from all the windows and everything, because sonic boom is around the corner and you don't want to get hit by that. All right, yeah, so this is the number which you can see. And talking about that powdery thing again, let me just have a look at it. So yeah, this is the thing. So right now we don't know whether this we don't know actually what the composition of the asteroid is precisely. So we don't know whether it's too much soft or whether it is not too much. So they have this beta value, which tells us what's the this porosity of this, whether it's porous or not, whether the asteroid is porous or not. The beta value defines the porosity. So if it is larger, then kind of you can say you can see like how it looks like. So here, no porosity, the velocity change will be 1.75 centimeter per second. So it will be like a hard rock. When it is going to hit, it will be causing this much velocity change. Then if it is microporous, then it will cause the velocity change of 1.87 centimeters per second. Then when it is a rubber like a thing, it will be causing a lot of change, and velocity change will be of 2.53 centimeters per second. So coming back to your question, yes, they have considered all the scenarios from being rock hard to being like a super soft rubber pile. They have analyzed everything, and they have taken those, maximum ranges to be in those safe range. So the velocity change of around 2.53 centimeter per second is in the safe range. So we'll get, after impacting also, right, we will be able to get to know what would be the composition of the moon, because we can actually measure the velocity change by measuring the orbital period, and once we get that, we can classify whether it was on the rubber pile, microporosity, or no porosity, and then we can identify some certain sort of materials which could cause that. And yes, so yeah, there is that. So that should have answered your question. And yeah, that is pretty much about it. Now I do have one video to show you guys which will sum up everything. Yeah, Draco feed is exciting, and I'll switch over to that, but let me just show you one video. It's a 3 minute video, so won't take much of a time, but it will summarize everything. So just enjoy this one.
DART is the double asteroid redirection test. The Earth is hit by asteroids and pieces of asteroids all the time. Every year or so, we get hit by things maybe the size of a table. The kind of object that DART is going to visit is an object that's about the size of the Washington Monument. Those kinds of objects hit us every few thousand years, and they would cause severe damage on a regional scale.
We chose to do this demonstration at a binary asteroid. It's called Didymos. This is actually approximately the shape of the main asteroid. It's called Didymos A, and its moon, Didymos B. What DART will do is DART will hit the secondary. When it hits the moon, it will change the orbit period. And when it changes the orbit period, it affects the timing of when the moon moves in front of or behind the primary.
Mostly what we're looking to do is change the speed of the incoming object by maybe a centimeter per second or so. So that's not very fast, but if you do it enough seconds in advance, you can cause it to miss the Earth entirely.
DART is a part of a larger collaboration called AIDA, which pulls in all the experts of the world who can help their governments predict and understand what it is that they can do and should do in the event that there was an incoming threat. The DART mission that APL is pulling together will be the first mission in that flight line.
DART is the first mission to fly the next Sea Ion engine. It is the first mission to demonstrate smart navigation, which means we're going to be guiding ourselves into the asteroid autonomously.
At about 4 hours out from impact, Smart Nav is kicked in, and what it does is it uses the imagery from the optical payload, basically the camera that's on DART, and from the imagery we are able to discern Didymos A from Didymos B. We have a targeting algorithm that differentiates the two, and we are aiming for Didymos B.
The other part of this is the propulsion system that we're demonstrating. The Next Sea propulsion system is utilizing a new generation of gridded ion propulsion technology, and it's what we're using to allow us to get to the asteroid, but also allow us a flyby of an object prior to our actual encounter.
For these vehicles to be able to supply the power for the electric propulsion engine, we needed higher power output. ROSA allows us to be able to have a very compact and light mass for launch and then deploy these really large arrays once we're out there in space.
Our planetary launch window opens on June 15, 2021, and will impact the asteroid in 2022. We're very excited to be NASA's first planetary defense mission.
So there you go, guys. That was it. So I guess now I should switch over to the Draco live stream if I can get. Oh, yep, we do have a live stream from Draco, and we are actually seeing something. So I'll switch over to that, and you can now. Yes. So there you go. So we are actually seeing something. So this light blob, it has identified this light blob. You can see it is closing down to the asteroid, and this is a live feed coming out of the Draco payload on the Dart mission. So this is how it looks like right now on the spacecraft, and this is the live feed. We are going to be developing a planetary defense system, and how cool is that? I can just, wow, we are doing something. Finally we are doing something sci-fi. Good luck, NASA, and I hope this mission is totally successful. We are around T-1 hour 15 minutes from the impact. It is right now a very tiny dot in the center, which you can see in front of your screen, but it will grow as it reaches near and near and near, and it will be able to distinguish. You will be able to see two dots, not the one. And yeah, yes, avenge the dinosaurs. Yes, indeed. All right, let me, if we have, yep, we do have it. We'll be starting soon, so until then you can just enjoy this. Although the stream is like very poor quality, literally very poor quality, but yeah, that's what we have right now. Okay, so hey, welcome all to the stream.
Asteroids have pummeled planets for billions of years. Now, one planet strikes back. For the first time in our planet's history, NASA will test an asteroid deflection technique. It's the first planetary defense method of its kind. NASA's double asteroid redirection test will intentionally ram itself into an asteroid and alter its orbit forever. At the crossroads of science fiction and reality, DART is part of our plan to defend planet Earth against potential future impacts. The test to protect the future of our planet takes place today.
Welcome, and thank you for joining us from Johns Hopkins Applied Physics Laboratory, home to the DART Mission Operations Center. I'm your host, Tahira Allen with NASA Communications, and tonight we're following the real-time journey of the DART spacecraft and its planned collision with Asteroid Dimorphos.
Very poor.
The Double Asteroid Redirection Test, also known as DART, is the world's first planetary defense test mission of its kind. At 7:14 p.m. Eastern, it will demonstrate an asteroid deflection technique known as kinetic impact. Rest assured, this is only a test. The asteroid DART intends to impact is not a threat to Earth now, nor will it be after the collision. We have live views of the action from space, so keep an eye on the DART cam in the lower left-hand corner of your screen. Right now, you're only seeing a black screen with a single point of light. That point contains two asteroids in it, Didymos with a smaller asteroid named Dimorphos orbiting around it. As long as we continue to receive these live views from DART, we're going to keep that feed up on your screen. As we get closer to impact, the asteroid will begin to take shape, and eventually Dimorphos will fill your entire screen. You'll also notice a countdown clock indicating how close we are to impact, and a progress bar that will check off key milestones along the way. Now, as we follow pre-impact operations, we invite you to join us as we check in with Mission Control for live updates and track DART's final milestones. We'll see two astronauts demonstrate what kinetic impact looks like in space, and we'll go behind the scenes at one of the observatories following DART's impact from Earth. You can participate in today's show tonight by submitting questions for our experts to answer live on air. Drop them into the stream wherever you're watching, or use the hashtag #PlanetaryDefender on social media. Now, we're a little over 70 minutes out from impact at 7:14 p.m. Let's now meet your co-host, Samson Rainey, joining us live from the Mission Operations Center. Samson, it's good to see you. How does it feel to be in the middle of the action tonight?
Hey, Tahira, I am feeling great. It is awesome to be back here after co-hosting DART's launch just 10 short months ago. How's the energy over there?
Wow, that's amazing, Samson. You know, everybody's super excited. I've been talking to some scientists and engineers before the show, and it's really just anticipation about what's going to happen tonight. So with that, could you give us an update on how things are going with mission operations?
Glad you're enjoying it there. This is going to be fun. So I mentioned launch, right? It was a huge event. NASA launches have become a staple of life for space aficionados. But there's never been anything like what we're about to see tonight, an attempt to impact an asteroid in near real time, the first attempt to change the motion of a celestial body. Just wow. If we hit that asteroid, Tahira, I think we're going to see a whole new side of this team that we've never seen before. Because let me tell you, since launch, these engineers and scientists have been eating, sleeping, and breathing this mission. This center has been like a second home for them as they've been monitoring the spacecraft's health.
I seriously can't understand what's wrong with the quality today. Literally, it's way poor. It's not like, you know, the asteroid image is poor. That is supposed to be poor, but or maybe they have intentionally downgraded the quality so as to make sure they, I don't know, if something goes wrong. So yeah, I don't know.
Trajectory correction maneuvers to aim Dart to within 200 meters of Didymos. Then they worked straight through to this morning to make sure that all went smoothly. Then they soldiered on to get us ready for tonight. And here we are, about an hour and 10 minutes from impact, and we're now in what's called the terminal phase, meaning that Smart Nav, the autonomous navigation system, is actively guiding the spacecraft as it was designed to do for its final 4 hours. I also received word minutes ago that Dart has reached another critical milestone. Draco, the eyes of Smart Nav, is able to detect Dimorphos. This is a major goalpost, I have to remind you, because up until now, Draco has only been able to detect Didymos, the much larger asteroid it orbits. The next major milestone we're waiting for is for Smart Nav to be locked on or targeting Dimorphos. We'll get more into what that means later. Lots more to come as we draw close.
I've already explained you all the steps of the guidance and navigation control, so you must be easier on that.
Know that we are detecting Dimorphos. Now, before we get any closer to impact, let's get to know our spacecraft and its mission. After a beautiful launch from Vandenberg Space Force Base on November 24, 2021, Dart has traveled over 400 million miles. And now, in just over an hour, we'll witness the spacecraft collide with Asteroid Dimorphos in an attempt to change its orbit forever. The Dart spacecraft is about the size of a vending machine and uses hydrazine thrusters for propulsion and roll-out solar arrays for power. It's traveling at about 14,000 miles per hour and will complete the last 4 miles of its journey in just 1 second. Dart is on a collision course with Asteroid Dimorphos, which is about the height of the Washington Monument and, more importantly, poses no threat to Earth. Dimorphos sits within a double asteroid system and is the smaller moonlet asteroid orbiting its larger companion Didymos. Dart has just one instrument on board, and that's a Draco camera, which is feeding images to its autonomous navigation system, steering it straight into the asteroid. Now, teams from around the world have worked hard to get us to this moment. Samson is standing by with NASA's head of science and Johns Hopkins APL's head of space exploration. Let's check in to hear more about the journey.
Thanks, Tahira. To help give us some insight into what it takes to imagine, much less attempt a mission.
So yes, Baba Yada, the relative velocity is around would be around 15,000 miles per hour. All right, so big people have come, so need to listen to them.
Thomas, I'll start with you. The mission this team has been through an intense journey, years in the making, and they're now on the cusp of doing the seemingly impossible. Impacting a tiny asteroid 7 million miles away from Earth with a spacecraft traveling 14,000 miles per hour. Why is it important for us to continue to push the boundaries of what's possible in space?
You know, what I always think is the world is made out of a box. Those are things we know, we can use, and a large space of things that are unknown. In that large space are solutions for problems of the future. There's new research, new understanding of nature. And we at NASA, we're all about moving that boundary back, moving it back to make more things useful for us, like Dart, but also understanding nature in a new fashion.
It's incredible, Thomas. Well, based on what we know tonight heading into this main event, you know, what are you thinking about our chances of impact?
Wow, I'm betting on the team. Betting on the team is always the right thing to do when it comes to NASA missions, whether it's this one or other teams we've had. The thing you just announced, that kind of seeing that little bump there in the image of that new kind of celestial body we knew was there, but now we've have it on the camera. It's just a step in that direction. I'm very optimistic.
That's awesome. What the team has planned for months, years ago is coming to fruition, and we're watching it live.
Absolutely. Just exciting.
Awesome. Thank you, Thomas. Bobby, you've been through so many white-knuckle experiences with space missions, most recently with the landing of the Mars Perseverance rover just last year. What is the mindset of the team coming to such a major moment in their career with the stakes being so high?
Well, teams like this prepare for the worst, but celebrate the best. And I think we're going to have one of those best nights tonight. There are, of course, many things that could go wrong in spaceflight, but so far this team's been on top of every possible problem. They've been ahead of it, and they just need to focus and push through and go for success.
That's awesome. I think from what we're hearing, the cheers coming out of the mock for this broadcast, I feel like we're on the right track.
Oh, yeah, absolutely.
Any pep talk or advice for the team heading into tonight that you gave them?
Well, I've been in the mock several times today talking with the team. They're calm, they're cool, they're collected. I basically told them just follow the data, trust in each other, trust in themselves. They've prepared for this moment for years, and so they know this better than anybody. And as
Hey
a team,
Jerry, you designed a Mars rover in 1987. That's great. And yes, this is also some concept of using asteroid as a fuel source to change the direction. Like, literally, you can kind of say burning it on fire, right? And then ejecta is used as kind of an engine to change the fuel. So this is also one of the ways. There are many ways, but right now they are testing the kinetic impactor way, where it will try to take the energy out of the system, so that it slows down, the orbit degrades, and the orbital period increases.
And they had some fun with it. Now, before we get to the video, I urge you to keep a close eye on Shane. He's going to be in the blue shirt and standing in for Asteroid Dimorphos. A white object is about to come crashing into him. That's our spacecraft. You'll notice how the impact of the crash moves Shane's position in space. This demo, much like Dart's test, relies on the energy transfer from a collision to change the motion of an object. The method, which is called kinetic impact deflection, is the technique Dart will test at 7:14 p.m. Eastern. Let's take a look.
So what I'll do, Shane's going to be the asteroid, and I'm going to be the NASA Dart mission. Or this CTB, more exactly, is going to be a spacecraft. I'm going to try to throw it, and we'll look at the effect of that mass coming at him and the kinetic energy transfer from the CTB to pretty good.
All right, now back on Earth. We're taking your questions live in just a few minutes. Send them in using the hashtag Planetary Defender and stand by. It's time now for our first status poll update. Let's head to Samson to check in on Dart's progress. Samson, how are we looking?
Hey, Tahira. We are entering the 60-minute mark until impact, and as you noted, the team is about to conduct a poll, which is essentially a status update to check that key systems are in working order. We're talking Draco image quality, Smart Nav, guidance and navigation, ground systems performance, everything that's anything to do with getting us to impact. All right, I think the poll is about to get underway. Let's start to listen in.
All right, so yes,
We are waiting for that poll to
will
begin.
take some time though. So yes, talking about, okay, all right, listen to the polls then. Will NASA have sound with video feed, and can camera be zoomed in? So sound is not there in space, although if you are talking about the impact sound, it won't be able to, um transmit it back to the earth if the microphone is even there. So because it would be destroyed, so of no use. And talking about zoomed in images, it has this you don't need a zoomed in image because you are going to the asteroid itself, right? So the image will get zoomed in and zoomed in as it goes near to the asteroid. So yep, that is supposed to happen.
Afterward, we should be hearing from Elena Adams, the mission systems engineer, to give us a summary of what we'll have just heard.
So this Sheldon, this is not a actual, a normal phone camera. It's a proper space camera which has its own thing. This is known as Draco. This is a feed from a Draco. It was used in New Horizon probe also.
Prior to impact. Woohoo! And we're seeing Dimorphos. So wonderful, wonderful. All right, let's do our poll. Image quality? Let's start with you.
Images are looking great. Dimorphos is coming in at about the same relative dimness as Didymos, so very consistent brightness between the two, and it's a stable track.
That's awesome. All right, Smart Nav?
Smart Nav is looking good. We're sitting at about 30 meters of projected miss distance. There is no movement right now on the bars for doing a maneuver, but we do expect that when we transition in about 10 minutes that we'll see a maneuver at that point.
Yeah, that's great. And at this point, because we have a stable track, we do expect to transition over at that time. So that's really good. Whew, that's good. All right, GNC.
GNC is nominal. We're ready to burn.
That sounds good too. And maneuver. All right. Let's see. Autonomy.
Autonomy is nominal. Heaters are cycling and no more fault rules.
All right. DSN.
DSN looks good, and we don't see any sign of rain. And ESA looks good as well.
That's good. And then ground system.
Ground system is nominal, and we have a clear vision of Dimorphos on the image display now.
Yes, it looks great. Thank you, guys. All right, one more poll after this, but in the meantime, we're going to hopefully transition at 15 minutes to locking. So stand by.
Great. So that was some poll. That was the most wholesome and most excited poll that I have ever listened to. So kudos to them. And yes, hi Marita, welcome. Hi Dave, Pratim, welcome to this stream. Yes, exactly. That's what I just heard.
Starting to see Dimorphos for the first time. It is looking great. It is just about the same dimness as Didymos as we expected. And so we are getting ready to transition. We have a stable track at this point. It's about 7 pixels in size. And yeah, we're ready to go.
It's great news, Lena. Thanks so much. I'll let you get back to it.
Thank you.
Wow, that's a great update. Joining me in reacting to that bit of news is Angela Stickle, planetary geologist and a Dart investigation team lead. Angela, you just heard the poll. You just heard Lena. Things seem like they're going really well. What are you feeling? What are you thinking?
Hey guys, so if you are just excited about this mission, just hit that like button and give your best wishes to this Dart mission. And guys, on this channel we do this only. I try to explain you and break down all the things for you. So if you are new to this channel and you want to understand what this Dart mission is all about, you can just rewind this stream a bit and you should be able to get all the information. And if you want to support me, guys, please do that. It would really mean a lot by becoming a member and a Patreon. This is the fuel. This is the bread and butter for this channel. So yeah, and for one-time funding, super chats are always enabled. So let's see, what do we have in store for us today?
Thank you, Angela. That's very cool stuff. Good luck with the rest of the evening.
Thank you.
Great. And while we wait, we want to invite you to celebrate the life of an important member of our DART team. Pulling off extraordinary events requires extraordinary people. And Ray Harvey was just that. A leader, an engineer, a friend.
Also, guys, where you watching this stream from, please type in the comments, and let's see what diversity do we have in here. And yes, on on this channel we do these live streams of the events, the launch events, as well as other videos also. So you can check this channel out. You will find it very amazing. I'm telling you, you won't regret it.
But also you had fun in the process.
I've known Ray probably since I started working here almost 25 years ago, and he was always like a good mentor and a sounding board for anything we were doing. I think everybody learned something from Ray, his leadership skills, how to treat people, how to work as a team.
Ray was a pretty amazing person. Even though he was fighting this terrible disease, he made it a point to be involved in all the rehearsals and all the activities going on DART. He led the mission operations team to the last few days of his life.
He was really hoping to make it to the end of this mission. He meant so much to this team and to getting us to this point.
It represents so many years of hard work of him and also the team, but him leading that team. And so the Dart Spacecraft is a tribute to Ray.
We are hoping that this experience kind of goes out to Ray and to his family. We will really miss him, and we already miss him.
Ray has touched so many lives. Even in the short time that I knew him, he was so generous with his knowledge, and he made you feel like you belonged. Ray, you will be greatly missed. This one's for you. Tahira.
Thank you, Samson, for that beautiful dedication. Now, if you're just joining us, we're under an hour away from the Dart spacecraft's head-on collision with asteroid Dimorphos. Dart's mission is a test of a planetary defense technique that could one day save humanity. Rest assured, the test poses no threat to Earth. The spacecraft is almost 7 million miles away from us right now, and you're watching a live stream of its approach to Dimorphos. It takes about 45 seconds for the images you're seeing in the Dart cam to make their way back to Earth. Any moment now, we should learn if Dart is ready to commit to impact. While we wait, I'm here with Andy Rivkin, Dart Science Investigation Lead, and Mallory D. Coster, Dart Impact Modeler. Andy, Mallory, while we wait to learn if Dart is ready to commit to Dimorphos, I can't help but wonder, why this asteroid?
That's a great question. The way that the double asteroid redirection test was designed, it was to measure the period change in a binary asteroid system. So we needed a binary asteroid, so that eliminates some number of objects. We needed something with a moon that was small enough that we could move it with a strike from a spacecraft, but not so small that we wrecked the moon. So when you kind of tick off all the possibilities, Didymos really ended up as the best choice and really the only choice that would provide a mission in this time period.
See, I want to go back to that. You mentioned having a moon that we could push but not destroy. Could you, now in pop culture a lot, we see that, oftentimes the idea is to just totally try to demolish the asteroid. Why have we chosen to not test that technique this time?
Yeah, the conventional wisdom for planetary defense is that you don't want to disrupt an object and blow it into a zillion pieces, but you want to keep it intact and just move it all as one piece. Because if you move it all in one piece, then you can keep track of it a lot easier. If you blow it into a million pieces, then some of them might still Earth, and you don't want to miss a thing.
Yeah, we might have more issues then. So we know that we have the perfect test
for
subject.
this, there's this series called Expanse, and there one asteroid was going going to the Earth, hitting the Earth, and there they demonstrated this nuke, warhead collision. So they destroyed the asteroid into like million pieces, small pieces, with the one strike of a nuke. And then when the other smaller pieces were formed, then other missiles were launched to destroy those smaller pieces as well. So it was like a very cool shot. And if we need to resort to nukes, then we need to make sure we do that. Only one nuke would not solve the problem at all. Even it would just enhance the problem. So yeah, there's how it works.
These fast impact velocities, and also these sort of extraterrestrial asteroid materials respond to deflection.
Wow, I mean, there's so much about tonight that we don't know, and it seems like your fun is just getting started, right, until after impact. So Mallory, Andy, thank you so much. And tonight, ground-based telescopes aren't the only one watching the action. A small cube satellite built by the Italian Space Agency was deployed by Dart 15 days ago and has been in the area to give us a bird's-eye view of impact. Here's more on Licia Cube.
Licia is a 6U CubeSat of the Italian Space Agency participating in the Dart mission, and it's also the first Italian satellite operating in deep space. Licia Cube mission objectives is to support DART in the documentation of the impact effects, in particular in terms of the ejecta of materials that will be released from the asteroid surface after the impact, and also imaging the non-visible side of the asteroid during its flyby.
Licia Cube will acquire images using its two different cameras, Leia, a panchromatic camera, and Luke, an RGB camera. Therefore, we can better understand the nature of the asteroid Dimorphos impacted by DART. By means of our Scientific Operations Center in SSTC ASI, we will distribute and process the images in order to make them available to the entire team.
We are here in Arbotech's Mission Control Center in Turin, from where, together with ASI, we monitor the status of Licia Cube. The batteries are charged, the radio is communicating correctly, and the navigation altitude is on the right trajectory. Everything is ready for the most important part of the DART mission, the impact with the asteroid.
DART is a global effort to prepare humanity for the unthinkable. Before the spacecraft can complete its mission, the autonomous navigation system must first confirm a lock on target. This is a key milestone that we should be hearing about soon. So let's go back to Samson for the latest for mission operations.
Hey, Tahira, we are less than 50 minutes out, and we just heard big news. We have reached the point where Smart Nav is now target locked onto Dimorphos. That progress bar should move to your right that much further, closer to impact. Very exciting. In the meantime, joining me is someone who worked on the instrument playing a starring role with this major milestone and basically all the way up to impact. Lisa Wu, mechanical engineer who helped install the Draco camera and built its cover. Lisa, thank you for joining me.
Thank you for having me.
So we just heard big news. We hit this target lock. It could have come fairly later than this, but we're in a good spot with this target.
How are you feeling? Yes, indeed, the 8th grade English class textbook has a good understanding of how asteroid works. I would give them that.
Could not be feeling any better.
Hey, now we can actually see the Dimorphos. We can see that moon. Can you spot it? I can, because there's a little white blob which you can see. So it's looking amazing now.
For the last 4 hours, a Draco imager, it's providing Smart Nav with that unflinching view of Dimorphos, about an image per second. It is the eyes of the spacecraft. Lisa, what makes this camera perfect for this mission?
Yeah, of course. So the Draco instrument is a very, very high resolution, narrow field of view telescope. The image quality, let's go back. Draco is a descendant of the Lori telescope, which might sound familiar because it took the very first pictures of Pluto on the New Horizons mission, which also might sound very familiar because that is an APL-led mission. So if you've ever seen the first pictures of Pluto, that is the amazing quality that we have on DART.
That's incredible heritage. And yeah, anyone who saw those images of Pluto, those were amazing, and that kind of ups the ante for what we're going to see with these pictures of Dimorphos, right?
Oh, yeah.
So we all know about a lot of us have smartphones with, cameras. We have cracks, smudges. How did your team make sure that this camera made it in pristine condition to get to this point?
Of course. So our flight hardware, including this instrument, was made in the clean room. Very, very high clean facility. In order to make sure that the telescope works, we had to put it through a lot of electrical testing, optical testing, alignment testing. We had to make sure it performs as we intended. And then not only that, you have to take this instrument and put it through all the environments that it will see through space. So we put it through vibration testing, thermal vacuum chamber testing, all to make sure that it performs and it will survive through space.
That's amazing. Test, 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 and test again, right?
Yes.
This is how we get to a stage like this. That is
exactly
awesome. That is great. Thanks so much, Lisa. The number of astounding technologies that are on board this spacecraft is amazing, but doing the impossible requires nothing less than the astounding, right?
Mm-hmm.
All right, Tahira, we have the technology. Clearly, we have the talent. Now we wait for history. Back to you.
All right, thanks, Samson. It feels good to know that we have locked on target Dimorphos. Now, earlier we asked you to send in your questions by using the hashtag Planetary Defender. And I am joined now by two real-life planetary defenders. We have Kelly Fast and Lucas Paganini, both from NASA's Planetary Defense Coordination Office. Let's dive into what you want to know. So, Kelly, Lucas, before I get to social media questions, we actually have a special question from a familiar face, especially if you're into football. So let's take a moment and hear from him.
What's up? I'm Joshua Dobbs, quarterback for the Cleveland Browns, and I have a question for NASA's Dart team. On the field, I have to use precision passing in order to get the football in the hands of my teammates, and at least I can see where they are. For NASA's Dart team, how are you able to aim a spacecraft at an object so far away?
You know, that's a really good question, Kelly, and I mean, we haven't really done this before. How can we aim?
Right.
Well,
But I have to say, Joshua does in a few seconds what we've taken, years to do. Just as he has to throw it where he knows that the player will be, throw his football where the player will be. Dart needs to end up where Didymos and Dimorphos will be, and so that was learned from astronomy, looking at through telescopes, calculating the orbit, and then the people who launched Dart to its destination navigated there. So there's just a lot more calculations involved, which Joshua does in his head.
Yeah.
And then there's this autonomous navigation. It would be like he had a football that could navigate itself.
Yeah.
And so we have that to lean on that he doesn't. And so that's what helps get to that destination.
All right, nice. I mean, it's very impressive. And so we have another question from Jonathan on Facebook, who wants to know, how can a small satellite like Dart be able to impact something as big and heavy as an asteroid and actually move it?
Right. And it's all about momentum, right? We have this tiny asteroid of about 160 meters, the size of a football field. And then you have this spacecraft, which is about 500 kilograms. So it's all about momentum, right? You have this massive asteroid and this tiny spacecraft. And how do you move it? It's all about mass and velocity. Since we don't have enough mass in that spacecraft, we have to really impact it hard, and that's why we're impacting it at 4 miles a second, which is outstanding.
Which is amazing. And I mean, we're actually going to get to watch impact live take place. And so that gets me to my next question. We have Metal Money on Twitter who asks, what is the size of the blast on the asteroid? Kelly, could you explain a little bit about that?
Well, and that's something that we're hoping to find out from this mission, because there's physics and calculations, but actually when you're dealing with a real asteroid that we haven't seen close up before, and what type of material might be on the surface, what the structure is, this is something that, like Lucia Cube, we hope to see as Lucia Cube flies by, to see what that blast was, how large it was, which will help those who are doing the modeling of how effective the impact was, and in changing the orbit, what all figures in, what Lucas just talked about, the mass and the velocity, but then also maybe that blast that is seen afterwards, the plume of material that we're hoping to see from Lucia Cube.
So how does tonight's mission play into the work that y'all do in NASA's Planetary Defense Coordination Office, Lucas?
Yeah, I would start by saying that this is a very important test. We're going to know if this kinetic impact is an effective technique to use in the case that there would be any potential asteroid en route to Earth. So definitely, for me, that's the most important thing about this test.
But then on top of that, there's finding the asteroids, because you can't go out and mitigate a possible threat if you don't even know it's there. And so NASA is very focused also on finding near-Earth asteroids with telescopes that survey the skies every night, looking for near-Earth asteroids, getting the orbits calculated, figuring out where they're going to be in the future to see if we even need something by DART, and then working to speed that up. NASA's working on the Near-Earth Object Surveyor space telescope that would look in the infrared and have a different perspective, complement the ground-based telescopes to accelerate things, just so that we know, is there a threat out there that we're facing that we do not yet know about?
Wow, I mean, it's incredible just to know the work that is already being done. It's good to know that we're building off of it, but it's good to know we've already got some people watching the skies. And so I have our next question from Alan on Twitter, who asks, how long does it take for pictures to reach Earth? Kelly.
Well, the time it takes light and then a radio signal from the spacecraft to come to Earth is 38 seconds, but then there's also the time needed to process the images, so a few more seconds on top of that. So under a minute, but still it's not instantaneous because it's a ways out there.
Well, that makes sense. I mean, but under a minute to get something back from space, I'd say we're doing pretty good right there. Right. So, Lucas, Kelly, thank you so much for everything that y'all are doing to keep our planet safe.
Thanks, Sahir.
And so it's important to note that tonight we're attempting something that's never been done. And with that presents many challenges to overcome. Here's what makes DART a first-of-its-kind mission.
The DART mission is a very difficult mission because we are trying to do something that hasn't been done
before. Guys, we
before.
are T-minus 39 minutes and everything is looking great. Yes, there are two objects and the smaller one is the target. We are looking good for the mission. Everything is looking good. The GNC is doing great, and yep, this is supposed to happen, which you just saw in the animation. So let's see, what do we have in store for us? And if you have any questions or so, you can ask me in the chat.
We are trying to hit an asteroid 163 meters wide, which is about the size of the Washington Monument, while flying at 6 kilometers per second, which is like going from New York to DC in about a minute.
There is no chance that this asteroid could ever hit Earth.
It's a very small asteroid. It's only about the size of a small football stadium, and it's almost 7 million miles away from the Earth. That's 28 times the distance between the Earth and the Moon.
There's kind of a limit on how much mass you can launch into space. You know, rockets are only so big. So our spacecraft is only the size of a golf cart.
Draco is the primary instrument on the Dart spacecraft. It is the camera that is going to be imaging the Dimorphos system as we approach.
When we first see the asteroid through Draco, it's just going to look like a pixel.
There's a star tracker on board that takes images of the stars and compares them to a known catalog to determine which way it's pointing in space. It poses the biggest risk because very, very small errors in this measurement can spell the difference between success and failure. And those measurements are going to be fed into the Smart Nav algorithm that's going to be making the autonomous course correction commands that will put us on an intercept course.
There is a very small probability that we don't hit the asteroid.
Even if we do everything right, our sensors work well, our spacecraft is doing well, we are looking, we're finding the asteroid, even then, we might still miss.
We're trying to teach a computer how to recognize an object we've never seen before.
And the way it does that is by taking pictures of the asteroid and then interpreting where it is in space and guiding itself to it.
The spacecraft is controlling itself. Smart Nav is guiding the spacecraft. And we have very limited ability to respond in that time. So it has to do it all by itself.
And at about 2.5 minutes out, we cease all maneuvering and we coast until we hit the asteroid.
It is going very, very fast towards the asteroid, traveling at 6 kilometers per second.
200 times faster than a car on the freeway. So when we hit, all of that mass, all of that momentum pushes the asteroid.
Even giving it a small nudge will allow it to change its course.
But if we did see an asteroid on track for Earth, this would be enough of a deflection.
It's like a bittersweet moment. Yeah, all this hard work just got destroyed, but that was exactly why we put it all together.
Of all the endeavors that we do for space and in space, this is probably...
Well, Mayank, you are spot on with that. Actually, there's this theory, and most of the scientists believe this only, that the moon was actually, the Dimorphos was actually the part of the asteroid itself. There was some sort of any event or something, might have hit with some other asteroid or something that caused the part of the asteroid to go in the orbit of the of that asteroid. So yes, it is definitely possible.
Space exploration is rooted in pushing past boundaries. Remember, tonight is a test, and we hope to make impact. Now that you've learned of the challenges today's test, let's head back to mission operations and get a status update on DART's real-time progress. Samson, how are we looking?
Hey, Tahira, we have 30 minutes to go until impact. As we heard earlier, so far so good. Smart Nav is now targeting Dimorphos. Thrusters are firing, maneuvering the spacecraft. Draco, Dart's eye, playing paparazzi with Dimorphos, providing Smart Nav with about an image per second. And this is a good time to remind you that what we're seeing on the Draco feed is delayed by about 45 seconds on account of signal delay and image processing. And coming up, we're about to see the team conduct a final poll, one last scheduled confab to make sure that all systems are go. And as we head to that, I have someone with me who knows a thing or two about ensuring spacecraft readiness and integrity. Betsy Congdon, DART's mechanical systems engineer. Betsy, thank you so much for joining me.
Thank you.
So you led the team that literally put DART together, is that right, Betsy?
Yeah, so my job is to make sure the engineers and the technicians all physically put all these boxes that you've been hearing, bolts and all onto a spacecraft altogether.
I gotta ask, with a mission so ambitious, how many hours, how many years, how many people? Do you have any idea at this point?
Oh, man. So, I mean, DART has been thought about for a long time, but really started in earnest about 5 years ago. We started building up the spacecraft and, in that assembly that I was talking about 2.5 years ago. And so it's been hundreds of hours, to make something like this possible. People with all sorts of talents. You've seen a lot of them today.
That's incredible. And so we're heading up toward another status update, as I said earlier. And as we all know, space is a unique and challenging environment. When you're assembling DART, what were the key boxes you were checking off of that very long quality assurance list to get the spacecraft to where it is right now and hopefully till impact?
So space is very hard, and so what we do is each individual component, Lisa was talking about this earlier, goes through its own individual testing, and then we put the whole spacecraft together, and we will check out the electrical systems, making sure all the boxes are working and talking to each other. We put it into a vacuum chamber, make sure it's going to work in space, put it through all the different temperatures it's going to see, and then put it on a shaker table and actually mimic launch. And so it actually goes through all of that as a full spacecraft as well as individual components. So we go through a lot of testing, mission operations, mission simulations to get to this point.
That's incredible. I mean, I don't know if you included, you mentioned so much array. Is that also accounting for the temperature fluctuations in space? That's another key part.
Yeah, so we have chambers here at APL that are specially built to take these spacecraft, put them into the vacuum of space, and run them through the temperature spaces that we're going to actually see.
It's incredible. How many times do you check? Is it like one test and we're done, or are you sometimes testing and testing?
Lots and lots of testing, and that's what makes it, so perfect. We're seeing these great images coming in because of all that testing and all of that work. So, you don't do anything once. You're doing it many times because once it's in space, there's not a lot of ways to fix it.
Right. Well, do you ever, think about that one panel, that one component that gave you a little bit of heartburn in the clean room, and you're up at night thinking, I think that thing is going to hold true up until the end?
Everything is looking really good. I will say, we had a lot of new technologies, which are really exciting. The ROSA solar arrays had never been integrated onto a spacecraft before, and so that was like a challenge, but one the team was up for, and now it's all ready and working perfectly.
All these new technology demonstrations, it only adds to the complexity of this mission and to, testing things. I wouldn't say even more so, but it's just as critical. The new technology, everything has to be so to make sure it comes.
Yeah, all of this new technology just requires extra testing, but that just gains confidence. You're seeing the team working through that, working through all these mission sims. So That's really what makes it exciting. You don't want to just do the same thing over and over. This is what makes APL a special place. We build these special spacecraft that, have never been done before.
A last quick question for you. It's got to be a little bittersweet that a spacecraft you poured heart and soul into is about to careen into an asteroid. How are you feeling about that?
I'm feeling great about it. It was designed to careen into the asteroid. It's meeting its destiny. So it's really exciting to see, and I can't wait for impact.
Well, it is serving a purpose. I guess that's why it's easier to let it go.
Exactly, very much so.
That is awesome. Well, I think we are about to get into that final poll in the mock very shortly. So we're going to hear that final 30-minute poll, and then we're going to hear from Lena Adams again, Dart's Mission Systems Engineer, to give us that summary of what we just heard, how she's feeling, how they're feeling in there. Very exciting stuff. This will be the final poll of the evening. We are awaiting that final poll.
This is Dart MSC on DT Mock. It is time for the last status poll. Yes. We're about, 7,000 miles from Dimorphos at this point, so yay. All right, image quality. How are we doing?
Still looking very good. Dimorphos still tracking along that same brightness predict as Didymos.
That's great. All right.
Maneuver complete.
Yes, thank you. All right. Smart Nav.
Smart Nav is looking nominal. We're at under 30 meters of projected miss distance right now.
Yeah, it's looking really good. Look at that. That's looking fantastic. Very excited. All right, GNC.
Yeah, GNC also looking good. We've been very excited to do those burns, so we've been waiting a long time.
Oh, this is great. Autonomy.
Autonomy is green. The heaters are cycling nominally, and we've had no new fault rules firing.
Okay, wonderful. DSN.
DSN is green, and ESA is green. Got plenty of margin. Looks good.
All right, ground systems.
Ground system has been helping a few users manage clients, but everything is going fine there, and we are green.
Yes, wonderful. Thank you, guys. Completes the poll.
There you go, guys. It's happening. T-minus 27 minutes.
Last one. All right, so Didymos is looking like itself. We'll see what Dimorphos is looking like soon. In the meantime, we're going to transition to precision lock at 20 minutes. That's our next milestone. So thanks all.
Hey, it's happening, guys. T-minus 27 minutes from the launch.
Right, we're about to hear
Everything
from
is
Lena
looking
Adams
good.
from the Mission Operations Center.
Hi, Samson.
Hi, Lena. That sounded very positive. How's it going in there?
Oh, it's going great. It's going great. We've locked on Dimorphos. We're maneuvering towards it, and yeah, everything is looking really good. We were at the time of the poll within just a few meters of projected miss distance, which means we were hitting towards the center. And at this point, we're coming back there about 30 meters off the center of the lit portion of Dimorphos as of right now. We've executed 2 burns. And everything's looking on track.
Oh, that sounds wonderful, Lena. Thanks so much for that, and good luck on the final stretch.
Thank you. Thank you. Have a good one.
Hey, Lauren. Welcome to the technician level. Thank you so much for becoming a member. It really means a lot. And yeah, no better time than this mission to become a member. And you won't regret the decision. So thank you so much for supporting it. I really, really appreciate it. And thank you so much, Srinivas, for 40 rupees too. It really helps me. Thank you so much, Srinivas Rao. And okay, this would pay for my coffee tomorrow for sure.
Exciting update, Samson. You just heard it. All systems are go.
Yo,
Mission operations confirm the spacecraft is on track for impact. But in order to hit the mark, the test must first locate its target. That's why Johns Hopkins APL engineer Michelle Chen helped develop new autonomous navigation techniques that will ensure a bullseye. Let's take a look.
Never in my life would I have thought I would take a couple $100 million spacecraft and crash it into an asteroid. My name is Michelle Chen, and I lead the team that is responsible for the autonomous navigation of Dart Spacecraft to hit an asteroid. The Dart mission is the first planetary defense test mission. Our goal is to hit and impact an asteroid to understand and study the momentum transfer so that we could potentially later down the road, if we need to, deflect an asteroid on its way to Earth. I am the Smart Nav lead. Smart Nav stands for Small Body Maneuvering, Autonomous Real-Time Navigation. Smart Nav, I always consider it sort of like the brains. And so the camera, Draco, is essentially the eyes. The algorithm has to identify and hit the target in the field of view of the camera. We're flying at over 6 kilometers a second. It essentially occupies a pixel up until possibly 30 minutes prior to impact. And then that's where everything gets really exciting. And so you could just imagine if it was a human being joysticking this. Because we don't know for sure what the asteroids look like, our simulation gives us the capability to use different asteroid shapes and asteroid objects to see that our Smart Nav algorithm performs against all these unknowns. We're super excited and nervous as well. I love pushing the boundaries, and I love the application of math into real-world problems, and then seeing it actually doing its thing. To me, there's nothing cooler than that.
If you're just joining us, we're about 24 minutes away from DART's impact with Asteroid Dimorphos. The spacecraft is flying at 4 miles per second, guided only by its autonomous navigation system. I'm here now with Tom Statler, DART program scientist, and Don Graninger, DART impact modeler. Tom, Don, thank you for being here with us tonight. We have some good news happening, but we did just hear about the challenges that DART is facing tonight. So, Don, could you tell us a little bit about what kind of uncertainty exists with a mission like this?
Yeah, sure. So what's really interesting is that until just, even a few minutes ago, I feel like we're just getting our first looks at Dimorphos. And so we have absolutely no idea what we're going to be impacting into. It could be covered in rubble pile. It could be just a completely different shape. We don't know until we really write up on that impact. And that's probably one of our biggest uncertainties on this.
I mean, but that's what really makes tonight so exciting. And so, Tom, could you expand a little bit more on how we will use this information in the future if all goes successfully?
Well, this test is really important to understand how we might be able to deflect asteroids in the future. And when we measure the change in the binary period of Dimorphos, and we will understand how the asteroid reacted to our kinetic impact. And then as we get deeper understanding into exactly what the geology was of that asteroid, that's the basic information that's going to help us refine our physics understanding of asteroids and our ability to...
The Dimorphos is actually visible now. It's more significant now. So can you spot it, guys? It's like it's moving with the darker spot, bright spot, bigger spot, I must say. So you should be able to see it. And talking about this mission is a type of one of the type to deflect an asteroid. So there are many types. There is one of those are the nukes also. Nukes should be like the last resort when it is too late to see the asteroid, too late to deflect an asteroid, and we don't have any other choice but to destroy it. Then only nukes should be used, and for that we need to develop missiles which can work in space, because otherwise it would be so difficult to do anything else. And so there are many ways to deflect an asteroid. One of the ways is this. There is like kind of burning the asteroid so that it, one of the subscriber actually, uh, um, you know. Told us that. So there is a type of thing where you burn the asteroid, it becomes kind of an engine, and then it just goes away. There are many ways, but yeah, this is one of the ways, and this is like, the most what should I say, capable and precise way to do a thing. So we are T minus 20 minutes and 37 seconds from the impact. We can see the distinction between the moon and the asteroid, although we don't know what this asteroid or the moon is made up of exactly. So we have this, what should I say, porous levels. Like if it is a rubber pile, if it's hard rock, what would be the change in velocity? If it's a rubber pile, what would be the change in velocity? So according to that, they will the orbital period will change, and hence you will be able to like know uh, what is the composition of the asteroid. So we are now waiting for the precision lock to happen. Precision lock is the target lock is, when you are supposed to identify what is the target. Like there are two targets here, kind of two asteroids here, right? The bigger one and a smaller one. Target lock is when you when your system identifies, yes, you need to.
Confirmation of precision lock.
There you go. We have the confirmation of the precision lock finally. So yeah, the target lock is when you can identify that the target is a smaller one and it is marked.
Go ahead, SN5.
We are precision locked and still tracking Dimorphos.
Yes.
There you go. That's what we want to hear, guys. It is happening. We are building our own planetary defense system.
I'm going to hear again from Elena Adams.
This is great. This is Dart MSC on DT Mach. So this was our last milestone. At this point, we're going to be working towards Dimorphos. I expect we're going to do some burns. We're about 4,500 miles away from Didymos and Dimorphos. So let's see what happens.
It is doing its job right now. And
Ground 41, C2.
Right, joining me now to react to that bit of good news is Lindley Johnson, NASA's Planetary Defense Officer. Lindley, you heard Lena, we are now precision locked, a lot of applause, things are looking good. And
yes, Boba Fett. So that's why they have these huge antennas here on Earth, right? The Deep Space Network, that is what we call it, and that is responsible for catching those signals which is coming in space. And in space there is no what should I say, network traffic, so it's very easier for the light to travel without any deviation, right? So yeah, kind of you can say the signal is not so, like the speed is 2G. You are getting kilobytes bytes per second of speed in these kind of things. So you can't but for this like we are getting the images per second, so speed is kind of good here, but in most of the cases speed is terrible.
Or will it be after impact, right?
No, that's right. This asteroid system is still almost 7 million miles away from the Earth. It's at its closest point in the orbit right now to Earth. So from this point forward, it's going to be moving away from Earth. So there's no chance of anything here. We've got to look for all the other unknown asteroids out there still to find what the hazard really is.
Thanks so much, Lindley. I'll catch you on the
audit amplifier. Actually, we will get some initial testing, initial results, maybe in the live feed also, but that is kind of rare. That's what I think of. But the thing is, they need to analyze the images and whatever data they are getting for weeks. The telescopes on Earth will be there and making sure they analyze and they watch this asteroid for weeks, and then we can get a proper measurement as to what actually happened there. But this the CubeSat which we have, is should be able to give us proper images of the ejecta as well as the impact side. We'll have to wait for the time for it to revert the images back to the earth, because it will take some good amount of time. It does not have a high gain antenna. Low gain antenna will be transmitting the image back to the earth. So yeah, it will take some time.
This is Lowell Observatory. Lowell is one of many observatories around the world that will be observing the Dart impact, NASA's first ever planetary defense test mission, to see how much a spacecraft impact can deflect an asteroid in its orbit. This is where Pluto was discovered, and we are still doing research in all areas of astronomy today. So let's go check it out.
Talking about the change orbit amplifiers, the thing is right now the orbital period is around 12 hours, and after the impact we are expecting an orbital period of around 11 hours and 45 minutes. So this will take some time for them to properly see. They can detect that yes, something has happened, okay, because the orbital period changed. They will be able to detect, but to precisely detect like what was the orbital period change, they will need some time. So yeah, you will get the initial details that yes, something has happened for sure. How good were the results? You'll have to wait for that.
In the days and weeks after telescope tube here. Up at the top is a secondary mirror. The secondary mirror up top there is what is focusing the light down onto the instruments and allows us to take images with the camera that's located down at the bottom. This is maybe one of my favorite hidden rooms at the telescope. We're like standing inside the telescope, underneath the telescope, 100 tons above your head, held up by this and this, which is cool. It's sort of, as you can see, the highest peak around here, just over 8,000 feet. I come up here for sunset, because sun setting right there, it's perfect. For Dart, we're going to be collecting images of the night sky. And typically an observer would be here in front of one of these consoles controlling the instrument and taking images like these as they're coming in off the telescope. Dart is really a sort of before and after experiment. We need to understand the system before the spacecraft intentionally impacts, and then we have to understand what the outcome of that impact event is. As we watch from the Earth, Dimorphos will pass in front of Didymos and behind Didymos. What we will be doing with those images is measuring the brightness of Didymos in those images and looking at how that brightness changes. And those dips in brightness allow us to measure when these eclipses happen and measure the orbit period of Dimorphos. And so you have essentially a fixed star field here. All the white dots are stars of different brightness, and moving through this field is Didymos and Dimorphos, which again, we can't distinguish them as discrete points of light, but we have that small object moving through the field of view. So after impact, we will then be able to go back and start observing intensely, looking for those mutual events, those eclipse events of Dimorphos passing in front of and behind Didymos. And on each one of these frames, we're measuring the brightness to assess whether or not it's undergoing one of these events where Dimorphos is passing in front of or behind, and using those to determine the orbit period of Dimorphos around Didymos. This is such a cool experiment. It's such a singular experiment. Using the ground-based telescopes like this one and others around the world to watch the system and see how it's affected by this impact event, because that's really what's going to give us the answer to what did Dart do at the time of impact. And that will be exciting to see how that evolves over the days and weeks following that impact.
Exactly. So yes, home cinema fan, the Dart is impacting the same size of the Great Pyramid. So yeah, almost the same side. Great Pyramid, I'm not so sure about it, but I did share some image regarding the scale. So it's just it's like if Burj Khalifa is 830 meters, the No, yeah, the smaller one, it's actually impacting the smaller one. So yes, it's almost the size of the Great Pyramid. And yes, not only the city, but it will destroy it will destroy the whole Earth if that size hits the Earth, because it's not like, the damage will be felt in a regional area, but when the sonic boom happens and the ecology of that area goes down, then the effect is actually felt for all over the Earth, and you don't want yourself in that situation.
Through space, and we'll cover the last 4 miles of its journey in just 1 second. Coming up, we'll hear the final updates from mission operators and witness the big moment live from space. Samson, you have the best seat in the house. How are we looking?
You're right, Tahira. Front row tickets to the biggest event in town, and things are looking good. We are T-minus 10 minutes to impact, and Dart is precision locked onto Dimorphos and zooming down the home stretch. Now, we have a lot to cover in the time we have left, and I'm thrilled to have with me Lori Glaze, Director of NASA's Planetary Science Division, with me for the ride. Lori, such a pleasure to have you.
Oh my gosh, I am so excited to be here.
So we are, guys, T-minus 10 minutes from the launch. It is happening. We will be able to see finally the demonstration of our planetary defense system, and I am way too excited for this one. I'm not so sure about you, but I am too damn excited.
Every time there's a marker that we meet a milestone, everyone is cheering and very excited. But there's also almost a sense of a calm confidence that with every milestone, everything's going, as planned. We're found and we locked on the target as planned, pretty much at the right time. They're looking at the brightness and the reflectivity of the object, and it's more or less what they expected. Everything is performing as expected, and so there's a lot of cheering and happiness, but just kind of a sense, hey, we've been planning for this a long time, and we've got it.
We've got this. We've been planning for this. We can hear applause left and right throughout this evening, all good signs. What are they focused on at this critical juncture, Lori? It is basically years of planning, 10 months of making sure we get to this point after launch, and they've been juggling a lot. Is there anything in particular that they are glued on as we enter this moment of truth?
Yeah, so the main thing they've been watching is, getting to that point where we could do the precision lock, where we had good enough signal coming back and enough confidence in where we are relative to Dimorphos that we could really do that precision lock onto the target. And it's hands off now, right? We're not, the spacecraft is going to drive itself, and really focused on that, that point where they could be precision locked. And they're also thinking about looking at and reassessing continuously what's the probability of miss, right? As you get closer and closer, that probability should get smaller and smaller, and it is. It looks really, really good right now.
It sounds like the game of thinking
it is
of
just
wondering.
getting bigger and bigger and bigger and bigger. And thank you so much, Michael Jeffrey, for always supporting me, for becoming a member, for being a member for so long. I also really appreciate your support. Thank you so very much.
Coming to an end. From 5 minutes to impact, there will be no more opportunity to send any commands to Smart Nav in the Mission Operations Center. The team will be purely spectators, the data coming in, and they are just waiting it out like the rest of us for the first time. Lori, this is huge both from an operational perspective and also an emotional one, isn't it?
Yeah, it is. I mean, you can imagine, I'm really excited about it, and I've been engaged with this mission for, the last 4.5 years that I've been in my current role. But this team has been working so hard on this for so many years, and they've put so much of their energy and their time into this, and so much planning and rehearsing, and it's a really big event for them to, like you say, just counting down and watching. At this point, there's not much else they can do but watch and see the fruits of all their work.
Yeah, I've gotten to know many members of this team over the past few months, and there's a lot of alpha individuals on there, right? You need a good mix of alpha people to make sure we get to this point. I can only imagine what they're feeling. Perhaps, like you said, a little bit of relief, a little bit of, can I let this go? I have worked for this moment so long, and now we can no longer do anything. That moment is just coming up.
Yeah, but I think they're ready. I think they're at that point. You know, you're getting some shots of Elena Adams, the systems engineer, and you can see the excitement in her voice. She's so ready to show the success of this mission.
This is awesome. 5 minutes out, which we're coming up on now. The team will be hands-off 2.5 minutes from impact. Smart Nav, which has been guiding the spacecraft autonomously for 4 hours, will also step away, stop any maneuvers. Dart will simply be coasting to its fate. This is blockbuster stuff, Lori.
Oh, yeah. Oh, yeah. We are there. Yeah.
I have front row tickets, and we are very soon about to open up these airwaves in the Mission Operations Center. We'll stay plugged in all the way through impact. Remember, at this point, 5 minutes out, no more commands to Smart Nav will be possible. The team is watching it just like you and me and the rest of us. All right, we've reached 5 minutes from impact. The final command opportunity to SmartNav has passed, and the team is simply watching that data stream in just like we are. Also remember, there is a 38-second lag for the data to travel to Earth, and also an additional few more seconds for image processing. It's important to note that. Should be hearing the chatter in the Mission Operations Center momentarily.
This is Dart MSC and DT Mach. 5 minutes till impact. 5 minutes till impact. We are at 1,100 miles away.
Oh, this is happening, guys. See how big it is looking right now. T-minus 4 minutes and counting.
Also, our window for sending any commands to the spacecraft is done.
Just wait and watch
Done.
what she does.
This is a great vibe in that Mission Operations Center right now, Lori.
It really is.
Guys, hit that like button and send your best wishes to this spacecraft to hit that Dimorphos. Whoa, just look at that. This is so cool.
I'm still having a hard time believing this is real imagery coming in near real time.
Same
Yeah.
here.
Yeah, but you've been watching it over the last, 30, 45 minutes go from just being a collection of individual pixels, and now you can actually see the shape and the shading and texture of Didymos, and we're going to see that same thing with Dimorphos as we get closer and closer.
Seriously.
This is
We
so
are
cool.
developing a planetary defense system finally.
Come into stark relief.
Absolutely.
A few seconds before impact.
Didymos. It's amazing.
T-minus 3 minutes. Whoa. It is... I just can't
The
describe it.
team
It
is
looks
standing just
amazing.
recognizing this moment years in the making. It is really nice to see them relax a little bit, get off from those computers that they've been glued to, and just appreciate this moment that's coming.
Yeah, and they've earned this. It's just great to see them there.
Wow.
This is so cool.
Lori, we hit another major milestone. We are now 2.5 minutes from impact, and SmartNav has stopped maneuvering the spacecraft. Dart is now coasting toward Dimorphos, and we hope into the history books.
Absolutely. This will be, I'm sure you've heard it many times tonight, humanity's first ever attempt at trying to move another celestial body, and also our first attempt ever to execute a mission in sole purpose of planetary defense. So what an exciting time. Yeah, and I'm starting to see Dimorphos start to come into view there. You can see it starting to take shape. I'm starting to see individual boulders on Didymos.
T-minus 2 minutes. Under 2 minutes now, guys.
Clarity of images
We're
there.
coasting on in. Our projected miss distance is going to be about 17 meters.
All right.
We are going in for that.
All eyes on this event. Space telescopes, ground telescopes from every continent on Earth.
Yeah.
Hubble Space Telescope, James Webb Telescope, and Lucy spacecraft will be watching it.
Oh, boy, we're getting close.
14,000 miles per hour, Lori.
14,000 miles per hour. And remember, 45 minutes ago, 55 minutes ago, we couldn't even resolve this,
minus 60
this
seconds
object
remaining,
in space.
guys.
And now you can see us zeroing in right on target.
And we're now dropping the clock, and we'll go by loss of signal to confirm impact.
Right.
Yes.
Yes. Imagine we'll get that loss of signal, and then we'll hear from Lena Adams again.
This is the only time when you are hoping that you get a loss of signal. I'm telling you.
Signal.
I think so. I think we're starting to see more.
T minus 30 seconds.
More resolution. In fact, look at that. Didymos has even gone out of the view. We're now just seeing Dimorphos.
This is remarkable stuff.
Oh my goodness, look at that.
Looks like control system settling down. Angular rates look really good.
You can actually see
some good pictures.
See those grains coming up now.
Wow.
So impact imminent now.
Come on, we can do better than that.
Starting to see those individual boulders there. You can see shadows of the various
It's
rocks on the
happening.
surface.
Finally, it is happening, guys. Oh,
Oh my goodness.
oh my God.
Unbelievable.
Yeah.
T
Looks to me
minus
like we're
10,
headed straight in.
9, 8. It is going in 7, 6. Oh God, 5.
Oh wow.
4,
Yeah.
3.
Oh my goodness. 8,
Yeah.
7,
Oh,
6,
wow.
5, 4,
Just look at
3,
that.
2, 1.
And
Oh my gosh.
whoa.
Oh wow.
Awaiting visual confirmation.
Just look at that.
All right. Let's see. We got it? Waiting.
And we have a loss of signal.
And we have impact. Equality for humanity in the name of planetary defense.
Dude.
Woo. Fantastic. Oh, fantastic. Oh.
That was so amazing.
What a moment. Very few words can really capture this moment. This is beautiful to watch.
It was like 15,000 miles per hour, and it was so darn bullseye, just at the middle of this Dimorphos, and finally everything is good now. I can't
They were
believe
getting
my
emotional
eyes.
at the dress rehearsal, and they're like, "This is crazy. We're getting emotional. This is not the real thing." I can only imagine what they are feeling right now.
Yes. Well, you can see them there on screen. They're all
Those images were just so good.
Hearing impact, the curtains close on Draco feed. That raw joy from the team, years of hard work and the weight of expectation lifted off their shoulders. This is amazing. This is beautiful. And Lori, really, this is a huge moment for the mission. Lots more work needs to happen in the days, weeks, months.
Absolutely. Now, as I always say, it's one of my favorite missions. Now is when the science starts. It just starts now. Now that we've impacted, now we're going to see for real how effective we were. We're going to train all of those ground-based telescopes.
Guys, we have a planetary defense system in place. Seriously. Just imagine that for a second. Sci-fi has come to a reality. We can say for sure. Almost we need to have some data right now, but the technology to do something of that sort of thing is in place. We just need to be more precise now, and how much precise we'll get to know from the data which everyone is collecting. The James Webb Telescope, Hubble Space Telescope, Lucy spacecraft, who is also going to the Trojan asteroids. And I'm just speechless now. We have done something really good as a space agency. for this planet.
An era in which we potentially have the capability to protect ourselves from something like a dangerous, hazardous asteroid impact. What an amazing thing. We've never had that capability before.
Thank you so much, Lori. Those are poignant last words. Tahira, history has been made. Back to you.
Wow. I mean, what an exciting day for the Dart team. And in case you're keeping score, humanity 1, asteroids 0. Now, I'm here with Nancy Chabot, Dart coordination lead. Nancy, talk about a moment to catch on camera. What is going through your head right now?
I mean, I'm just thinking, wow, that was amazing, wasn't it? I mean, those images, you just got closer and closer, and sort of we've been planning for this moment. We've been talking about it for years. At APL here, we've been working on this since 2015, and I knew, I've been talking, these are the images that we're going to see, and they're going to be spectacular. And I think even then they exceeded my expectations of just zooming in like that, and, you know, it really is just such the team accomplishment, and to get to this moment over so many years. And I don't have to talk about it as coming anymore. It's happened now. We have done this.
It's happened, and it is just incredible that as humans, like, we have done this. We did this. And Nancy, do you have anything you'd like to say to the teams who made tonight possible?
Oh, I mean, I don't need to say anything to the teams because I know everybody like me is really proud to be part of this, right? Proud of this thing that we've been working on for years, you know, and even before 2015, internationally,
Guys,
people wanted to.
We have finally avenged the deaths of millions of dinosaurs, and finally we can, you know, guys, we can literally now feel safe here on Earth, because we were like, someday asteroid will come and then destroy everything. Now we have a system in place which can protect us. Literally a defense system in place. Solar system will not kill us. So yes, it is. I'm just hoping that they were like precise enough for this moment, right?
This is a big deal, and this was a really hard technology demonstration to hit a small asteroid we've never seen before and do it in such spectacular fashion. But I know other scientists on the team like me are already pointing at those images being like, did you see that boulder? Did you see that smooth area? Did you see the shape? What does that mean? And Lychee Cube is like flying by right about now. They're close approach, like taking images, and they're storing them, and we'll get those in the next days. Telescopes here and in space are looking. They're looking at the brightening of the rock that's thrown off from that spectacular collision that we saw. And this is going to go on for weeks. And so there's still a lot of excitement to come, but nothing to take away from this moment.
Yeah, this is just the beginning. It looks like everybody is celebrating here in Mission Operations. I think I just saw Bill Nye there. And so it is a huge day for this team, but also for humanity. You know, Nancy, you mentioned earlier about some of the international collaborations. And could you give us an idea on kind of the scope of Dart's mission, right? It's not just us in the United States that's focusing on this. So can you expand a little on that?
Yeah, I mean, planetary defense is really an international issue. We are all on this planet together, right? I mean, and I think it's been so great for this mission to really support and embrace that international cooperation for planetary defense so that we can maximize what we learn. And this idea came about from international scientists talking to each other, working together, you know, in order to make this moment happen for NASA's Planetary Defense Coordination Office, building the spacecraft here at APL. But really, scientists around the world are ready to study the, what did we do to Dimorphos? But more importantly, what does that mean for potentially applying this in the future? I mean, DART really is just the start. It's just the first planetary defense test mission. It was spectacular, and it's accomplished, and we'll figure out how effective it was. That's really what we're going to learn in the next weeks to come. All right, we hit this asteroid. Now, how effective was that at deflecting it, and what would that mean for using it?
Yeah, there's still so much to unpackage here. And so we have a special guest who is wondering, you know, more of what's next for this big mission. So let's hear from her now.
Hey everyone, I'm Danny Hansen, American Paralympic rower and hydro athlete. And first, I would like to congratulate the entire DART team on crossing the finish line. So congratulations. And with that, here's my question. Now that DART has impacted, how will you know if the spacecraft has actually changed the asteroid's orbit?
That's a good question.
Yeah, I mean, so this is a double asteroid system. So all we've done here actually is change slightly how Dimorphos goes around Didymos, right? And the telescopes on the Earth have studied this for years. So we knew it used to be 11 hours and 55 minutes. What is it going to be now? And so the telescopes are going to measure that period change. And they're so good at this. They've done it for decades already to get us to that point. And they're going to work for the next weeks and make that measurement. And when we have it, we're going to be sure to share it with everybody to see how much we did deflect this asteroid with the Dart collision.
Wow. Well, Nancy, I mean, it's time for you to celebrate. So congratulations on everything tonight, and go Dart.
Oh, go Dart. This was spectacular.
Yes. And so we have Samson standing by in mission operations with two very special guests. Let's hop over there and see what's going on.
Thanks, Tahira. I have the pleasure of introducing NASA Administrator Bill Nelson, who has a special message for us.
Hey, congratulations. Boy, the Dart team, you really did this one very well. It's been a successful completion of the first part of the world's first planetary defense test. And there were years of hard work. There was a lot of innovation and creativity that went into this mission. And I believe it's going to teach us how one day to protect our own planet from an incoming asteroid. I really look forward to learning all about what's happening from the observatories so they can tell us about the changes in this asteroid's orbit. So thank you to this international team. We are showing that planetary defense is a global endeavor, and it is very possible to save our planet.
Yes, indeed.
All right.
Dude, that was... I'm just in awe, and I'm just seeing all the images again and again. Let me just... what do we have in here? Not... Okay, so we don't have anything there, but yeah, those images were so awesome. Dude.
And just realizing all the science that we're going to learn. But the best part was seeing at the end that there was no question there was going to be an impact, and to see the team overjoyed with their success.
That's beautiful. What does this mean for NASA? What does this mean for planetary defense?
Well, NASA works for the benefit of humanity. So for us, it's the ultimate fulfillment of our mission to do something like this, a technology demonstration that, who knows, someday could save our home.
Very powerful. Thank you, Pam. Ralph, you were in that mock for the moment of impact. We've seen a lot of major milestones in APL's history in space. We're talking the first flyby of Pluto, the first mission to orbit Mercury, and now the first spacecraft to impact an asteroid. What was the moment like for you in there?
It was incredible to see how so many years of hard work and creativity resulted in a direct hit of Dimorphos was just an adrenaline rush. I'll add that I've been at the lab now for quite a few years, and I've been involved in a lot of missions and achievements, and never before have I been so excited to see a signal go away and an image to stop.
Ralph, I'm going to give you both a treat right now. We're going to play that replay of impact on our screens right now so we can enjoy it again. Ralph, what does this achievement mean for Johns Hopkins APL? Huge, right?
Oh, it is huge. And in fact, if you'll excuse the pun-like statement here, the impact on APL, as it was on Dimorphos, is immense. This is exactly
just enjoy these images, guys. Just look at that. It's coming now. It's like good frames per second, and just look at that. Just look at that. Whoa.
Of the entire Dart team and APL.
And so, yeah, Mayank, talking about when can we expect information of from Lycia Cube, I'm not so sure about it, but yes, it is supposed to look out for the ejecta cloud, which has happened now, as well as take the images of the impact site. So yes, that is also something.
Light, and now they are real objects to us, which is amazing.
Never before seen up until today.
That is amazing. You know, it's just as good the second and third time.
There's that drop off, knowing we made impact.
Fantastic.
Well, there you have it. A lot of pride here tonight, along with the promise of big things to come. And with a successful DART impact, that will do it for us today at the Mission Operations Center. Back to you, Tahira.
Amazing. I mean, today is a fantastic day. And DART is just the beginning of a global planetary defense effort. In 2024, the European Space Agency's Hera mission will conduct follow-up observations of asteroid Dimorphos and measure in great detail DART's kinetic impactor tests. Let's take a look.
The DART impact is going to be an incredible moment, something we've been looking for over 17 years. My name is Jan Carnelli, and I'm leading the Hera mission for the European Space Agency. The deflection by DART will be measurable from ground with telescopes. However, only with Hera coming up close and inspecting the asteroid will unveil all of those parameters that will allow us to plan for a deflection mission if one day we need one. This is the propulsion module of the Hera spacecraft that will take us to Asteroid Dimorphos and will allow us to study the results of the DART impact. The propulsion module is being built here in Italy and then will be sent to Germany, where it will be mated with the instruments and the rest of the spacecraft to be ready for launch in October 2024.
We started designing and conceiving the whole mission and the spacecraft about 2 years ago, and we have a launch date to meet that is a fixed date in October 2024. So it's challenging, but we're making it possible. You could say that Hera is really 3 space missions in one. We have one, the main spacecraft that we are currently building at OHB in Germany, but we also have 2 smaller missions that are spacecraft in their own right. Those are the 2 CubeSats, Juventus and Milani.
The CubeSat I'm working on is Milani, which will perform spectral measurements and dust detection following the DART impact. My name is Margherita Cardi from TEVAC International in Italy. We will work alongside the other CubeSat, Juventus, which will perform kind of an X-ray of the asteroid to understand the internal structure.
This is going to be the first time that we have CubeSats on board an ESA spacecraft. Once we arrive there, we will be deploying the CubeSats in order to complement ESA's scientific observations, taking more risk, but also trying to have higher rewards.
The CubeSats will be installed on 2 panels that will be mounted on each side of the structure of Hera. They are just the size of shoebox, however they contain complex technology which will really allow to bring added value to the Hera mission.
Hera and DART represent a fantastic international collaboration between NASA and ESA. The 2 missions complement each other and will validate an asteroid deflection technique that we could use in the future to protect planet Earth.
There you have it. Tonight, we've ushered in a new era in planetary defense. At 7:14 p.m. Eastern, the DART spacecraft targeted and collided with Dimorphos, showcasing a technique that we could use if a hazardous asteroid is ever on a collision course with Earth. Even though impact is over, the process of moving the asteroid is still going on as we speak. Over the next days and weeks, we'll be monitoring Dimorphos from all angles, tracking its change in orbit with ground-based observatories, studying the impact crater and ejected materials with space telescopes, and we may even get images from missions like Lucy, Hubble, and Webb. Now, don't miss a beat. For mission updates, follow Asteroid Watch on Twitter, NASA's Solar System on Twitter and Facebook, Remember, impact was just the beginning. Science and images will be rolling in soon, so stay tuned to nasa.gov/DART. We'll be back at 8 p.m. with members of the team to capture reactions and celebrate this historic event. So join us soon on nasa.gov/live. And for more updates on the Artemis and rollback operations happening tonight at the Kennedy Space Center, head to nasa.gov/Artemis-1. Thank you for watching NASA's coverage of DART Impact from Johns Hopkins Applied Physics Laboratory in Maryland. We want to give a special thanks to all of our guests for participating in today's broadcast, and a big shout out to my co-host Samson Rainey for keeping us keyed into the action. Go DART, and good night.
Finally, guys, we have a system in place which can defend us, which can make sure that not only humanity but the Earth survives. Whoa, that is something to just think about it. I'm just speechless, totally speechless today. Like, how are we so late to not have such a system in place? Like, these kind of things are so what should I say, important to do, but no worries, we have achieved now, and hopefully from now onwards it just accelerates. I'm just hoping that now. Okay, all right, we have anything else? Exactly, thank you so much for your service. And yay, see this, SpaceX is actually congratulating, although yeah, SpaceX was the one who launched the spacecraft, so yeah, that was a thing. So there you go, guys, the DART mission is finally successful, and we have absolutely bullseye indeed. Rocket Lab is congratulating. Wow, each and every company is congratulating. Firefly Aerospace is there. JWS observation observing Didymos using an IR cam, which you will see certain images. So yeah, this was the last image which we got from the DART mission. Okay, so what is this? It's kind of a unique feature. Maybe just a lighting sort of a thing, but yeah, it's a good thing to see. We'll have to hit and see. These the science is just beginning to come out. We'll see so many things happening, and just wow, I just don't have any words to describe like what just happened right now. Oh man, this was something for sure, for damn sure, this was something. Oh, I just don't have any words. It's like 5 a.m. here right now, but still, I don't have any regret for me just trying to stay awake till 5 a.m. But right now, after the excitement has just died down now, and I'm also on that stage of dying down. uh, I can't take it anymore, but yes, it was indeed a thing to watch, and I'm so happy that I covered it, and hopefully guys, you were able to see and understand like what actually happened here. So if you didn't, let me just repeat once again so that you can have a look at it. So yes, this was a system. So this was the thing. So there was a Didymos and the Dimorphos. See, this is a thing which I do in my normal streams also. Like before any major thing happens, I try to explain what is going to happen. So this happened. The Dimorphos got impacted by the Dart spacecraft. So this is still alive. So there was a Dart spacecraft, and this is Lycia cube also was there, and this is still alive, and it is slowly and steadily coasting towards the impact site. It will be able to and image the ejecta, what is coming out of it, as well as the impact site also. So we'll have to wait for this little guy to do its job and get some images out of it. So we'll have to wait and see about that. And yes, this is oh god, this Dart mission, she is no more, unfortunately, but thank you for your service. You did a great job. Yes, this is the Dart spacecraft when she was here on the Earth. Okay. And now I also, like, sorry, explained different things about how the navigation and everything looked like. I don't want to repeat that, but yes, this is the thing which we hit. It's almost the size of the Great Pyramid of Giza, even bigger than that. So you can imagine the size of it which we have actually hit. So yeah, so we were observing, it has hit, the ejecta has gone out, and it's still hopefully in the orbit of the Didymos, but we'll have to wait and see, analyze for this little guy to come and give us some good images of the impact site. All right. So I guess that should be it for me to also. Thank you so much for tuning in, guys. And yes, guys, don't you worry about the images and updates. You can just follow me on Twitter. Here, this is my Twitter at the rate Rocket Gyan, this one. It's in the description also. I'll post all the updates regarding it, what is supposed to happen, any images or anything which will happen. So yeah, you can just come here and we'll have a chat. So also you can tag me on Twitter for anything. And yes, this is me getting a picture with the ISRO chairman. I was very lucky, and he was very humble for getting a picture. So yes, this is a thing which I do. So if you are into space and rockets and everything, you just hit that subscribe button right now, and you will not be disappointed. So thank you so much for tuning in. It's almost 5:30 a.m. and I haven't slept. I have an office tomorrow at 9. Dude, tomorrow will be a tough day for me. So thank you so much for tuning in. And yes, I will come back in just 3 days from now for on 30th of September for Firefly Aerospace launching, hopefully making into orbit this time. And yep, we'll have another rocket company joining the elite club of space. Okay, thank you so much for tuning in. Until then, this is Priyanshu Roila. You just saw Rocket Gyan. Stay safe, stay healthy, and bye bye.